Hey folks, you are on your test review. This is it. We are down to the end, That's it. Yay. Last podcast of chemistry. Fabulous. All right. We're just going to run through these really quickly. Positively charged particle made up of 2 protons and 2 neutrons being released is an alpha particle. And the electron released when a neutron breaks apart into a proton and an electron, that is called a beta particle, right? Abbreviated beta. And this one has got to be gamma, right? So that's a gamma ray. Remember, a gamma ray is light. So what's the charge on a gamma ray? Right? It is 0. There is no charge because it's light. Okay. What's the change in atomic number when an atom emits a beta particle? Well, if you emit a beta particle, then you would be going from, let's say, an atomic number of 6 to an atomic number of 7, like we do with carbon-14, right, as an example. So we gain 1. And with an alpha particle, you lose 2. And a gamma ray, it has no change. Okay, because, again, it's light. What's the charge in atomic mass? Well, beta particle, it has some, but it's almost none. All right, so we view it as none. So when we're actually tracking the amount of mass in the thing, we treat it as none. Now, there is some. There's a very, very tiny bit that is converted to energy that's lost, but we're just going to look at it and say it's none. All right, alpha particle, you are losing a mass of 4 atomic mass units. And a gamma ray, there is none here at all. Okay. All right, so let's go off and do this little chart. Let's see, type of radiation. Our symbol, we have an alpha particle, we have a beta particle, we have a gamma particle. Our charge for an alpha particle is +2, for a beta particle is -1, and for a gamma particle, it has none. Your isotope notation, we draw the alpha particle, and then we draw a 4 and a 2. And a beta particle, we draw a 0 and a -1. And the gamma ray, we just put 0 and 0. Right. Now, your penetrating power is kind of low. Right. It can be stopped by clothing or paper. This one is medium. So it'll go through 1 to 2 millimeters into a solid object like your skin. Right. It will go through your clothing. And your gamma rays will go right through you. Okay, so we need lead. We need a few inches of lead or about 10 feet of concrete to stop gamma rays. Right? This is why they put so much concrete on top of Chernobyl. All right, the amount of time for half of the atoms in a radioactive sample to decay is called of course, it's called the half-life. And the process by which things are decaying is called radioactive decay. Right? Radioactive decay. And guess what? That's the answer to number 10 as well. Radioactive decay is the breaking down of a radioactive element. All right, number 11. Alpha radiation is a stream of helium nuclei, which means they're positively charged because it's protons. Beta radiation is a high-speed electron, so it's negatively charged. And whenever an element undergoes decay, it turns into another element with an atomic number 2 less. Well, it's turned into 2 less. That has to be an alpha particle. And during what type of decay a neutron decays into a proton and an electron? Well, that is beta decay. We talked about that. That's kind of a goofy one. Okay. The more stable a nucleus, nucleus is, the longer the half-life. Right? Alpha particles can be stopped by a piece of paper, and beta particles can be stopped by a thin sheet of metal, and it takes a thick metal sheet, all right, a few inches thick of lead to stop gamma rays. Alpha particles, beta particles, or gamma rays travel at the speed of light. Well, the only thing that can travel at the speed of light is light, and gamma rays are light. So that works fine. And gamma rays are also not affected by a magnetic field because they have no charge. Okay. An alpha particle is actually the nucleus of, when we talked about this, it's often looked at as a helium nucleus because it has 2 protons and a mass of 4, which is what helium does. Now, beta particles originate in the nucleus of an atom, specifically by a neutron that is breaking apart into a proton and an electron. Radioactive processes occur until a stable element is formed. Remember, we did this with U-238 until it formed lead, specifically lead-206. Explain what happens in a chain reaction. Well, the concept of a chain reaction is, think of it, if you will, like you start a fire burning and it just keeps burning because there's lots of fuel there, right? And you only started it with a little bit, but it feeds on itself and it generates more heat. Well, that's kind of like a nuclear chain reaction as well. The example that we used was we stuck one neutron into a reaction, and that reaction produced multiple neutrons, all right? And those multiple neutrons that are produced can then go back and spawn more reactions, okay? So, and that will just keep on happening. And an uncontrolled one would be a nuclear bomb. Define fission versus fusion. Fission we talked about like a fissure in a rock where a rock breaks apart. And fusion we talked about like we take and fuse 2 bones together in your neck to hold them permanently together. Right? So fission would be something breaking apart, like a large atom breaking apart into 2 smaller atoms, all right, that are similar in size. All right? Whereas fusion is 2 small atoms coming together, and they come together and they bond together and they make 1 atom that is bigger. Okay, so that's the concept of fusion. What does neutron absorption accomplish in a nuclear reactor? Well, part of the problem is if you have that chain reaction going on and you're producing lots and lots of neutrons, you're going to have an uncontrolled reaction. So the neutron absorption is done by the control rods, and they absorb neutrons, right, to slow down the reaction and to control it. Now, control rods are usually made out of, well, there are lots of answers here. Right? We talked about carbon. We talked about silver. There are others as well. They're cadmium. I thought of one more. Boron is another one that they're made out of. All right? And these all absorb neutrons. So that's one of the reasons control rods are made out of them. Right? What instrument is used to check for current radiation? If we want to check immediately, what's our radiation right now? That's a Geiger counter. However, if you want to know how much you've been exposed to over time, like you work in a nuclear power plant and you're going to wear a badge that figures out how much you've been exposed to over time, that is called a dosimeter. Okay, we talked about radiation therapy, for example, using radium implants, all right, to go and irradiate or kill cancer cells. 3 beneficial uses of radioisotopes. Well, one is killing cancer. One is detecting cancer. We talked about thyroid, how iodine-131 could be put in your system, and then they can see your thyroid glands without cutting you open. All right, so detect, T-E-C-T, detect cancer. All right, we can preserve food with it. We can get electricity from it. And you can also use it for weapons, which can be viewed as a positive or as a negative. Right? Where was the worst disaster? The worst nuclear accident? That was in Chernobyl. And that was in 1986, and that was in the Ukraine near Belarus. Now, there was also one at 3 Mile Island in the United States, but that didn't kill anybody, and there was also one in Japan back in 2011. That killed some people, but it was nowhere near as big as what happened in Chernobyl. All right. The half-life of a given isotope can be altered by heat, pressure, or some other physical means. Nope. Half-life is the half-life, and you can't change it no matter what you do. All right, speaking of half-lives, let's go and calculate a couple. These are all new problems. All right, so I'm going to draw my little chart here where I have half-life, and I have time, and I have amount. And my half-life always starts at 0 at time 0, and we start with 100 grams of my substance to begin with. All right, and my half-life is 2.4 minutes. All right, so that's one half-life. And after 2 half-lives, it's 4.8 minutes. And after 3 half-lives, it's 7.2 minutes. Oh, notice I'm where I want to be, so I can stop now. It only took me 3 half-lives to get there. All right, so what happened to my amount? Well, every time I went through, I divided it by 2. So it's 50, so it's 25, so it's 12.5. So I have 12.5 grams of my substance at the end. All right, let's look at palladium. This has a half-life of 3.6 days. Looks like I'm going to have a lot to write here with time, with my amounts, right? That's my time, that's my amount. And my half-life always starts at 0 at time 0. Wonder how many of these I'm going to have to do. All right. Let me just write these numbers down. 3, 4, 5, 6, 7. All right. And let's say I have my half-life of 3.6 days. So I put my 3.6 in here. And this is in days. Right? So it's saying how many atoms would be left after 21.6 days. Let's see how far I have to go. That's 7.2. That's 10.8. That's 14.4. That's 18.0. And that's 21.6. So I finally figured out where I had to go. I start with 6.02 times 10 to the 23rd atoms. That's 1 mole. Right? So let's go and see how much is going to be left. Well, this is 3.01 times 10 to the 23rd. This is 1.505 times 10 to the 23rd. This is, okay, I'm going to not do it in proper scientific notation. 7525 times 10 to the 23rd. These are all going to be times 10 to the 23rd. 0.37625 times 10 to the 23rd. And then 0.188125 times 10 to the 23rd, and then 0.0941 times 10 to the 23rd. Now if I go and I make this into proper scientific notation, this becomes 9.41 times 10 to the 21st molecules, or atoms. And that's how much I have left. All right, let's look at this one. Different way to phrase something, but the ideas are all the same, so there's nothing exciting here. Half-life, amount, time, amount. Half-life is 0, 0, and I'm starting with 10 grams. Okay, so I start with 10.0 grams, and it says how much would be left after exactly, how much would have decayed, how much would have decayed after 3 half-lives. So let's see. So we have to be careful here. We have 1, 2, 3 half-lives. So we don't have to worry about the time because that's not important. But this becomes 5, this is 2.5, and this is 1.25 grams. So we have 1.25 grams left. It's asking us how much decayed. So that would be 10.0 minus 1.25, which would be 8.75 grams would have decayed, and we would have been left with 1.25 grams. Okay? All right, let's try another one. We are starting with 128 milligram sample. Where's my little mouse? Here you are. Thank you. So let's put half-life up here, and time, and amount. All right, and we start at time 0, because we have half-life 0, and we're starting with 128 milligrams And we want to end up down here somewhere at 2 milligrams. So let's see how far we have to go. Just don't know how many lines we have to draw, so we'll just draw some lines, and so where we end up. Did I have enough? Maybe. That's 64, that's 32, that's 16, that's 8, that's 4, that's 2. Okay, so here's where I stop. Right? And this is going to be 1, 2, 3, 4, 5, 6 half-lives. Okay, and it took 24 days. Well, if it took 24 days and I divide by 6, 6 goes into 24, 4 times. So that means my time up here is 4, and this is days. So that is my half-life. My half-life is going to be 4 days. Let's make sure that works. That's 4, that's 8, that's 12, 16, 20, 24. Cool, that works. All right, let's try this one. At time 0, there are 10 grams. So let's, this looks like I'm going to have to put a lot of information in here. All right, I'm going all the way up to 7 days, and there are, half-life is 24 hours, so that's 1 day. All right, so my half-life, my time, and my amount. 0 times 0, I have 10 grams. All right. So let's come down here at half-life 1, that's time 1, because it's 1 minute, and that's 2 minutes, and 3, 4, 5, 6, 7, and that's how far I have to go, 3, 4, 5, 6, 7, and that's 10, that's 5, that's 2.5, that's 1.25, that's 0.625, that's 0.3125, that's 0.15625, and that's 0.078125. Okay, so it's saying how much will be present at the end of 1 day? Well, 1 day, there's 5 grams left. After 2 days, there's 2.5 grams left, and after 7 days, there is 0.078125 grams left. Obviously, I ignored sig figs, but you get the idea. All right. Got a couple more to go. We have 100 grams of an isotope with a half-life of 36 hours. All right, so we have half-life. We have time, we have amount, zero, zero. We have 100 grams. We have 36 hours, half-life of 36 hours. All right, so we're going to just work our way down this one. We are, let's see, how much time left before 50 grams remains? And then for 313 grams. So 50 grams is simply, that took 1 half-life for 36 hours. But we have to keep going. 12.5, 6.25, 3.125. There we are, right there. All right, so let's do our time. That's 72, that's 108, that's 144, and that's 180. All right, just to be, you can check this way. 3, 4, 5. This is 5 times 36. 5 times 36 is 180, so that's just another way to do it. All right. How much time will be required to lose 75% of your radioactivity? Okay. Well, if I look at tritium, I have my half-life, I have my time, and I have my amount. Right? So since we're dealing with percentages, let's just think about this. At time 0, we have 100% of our stuff. All right? At our next time, we're only going to have 50% of the stuff. And at the next time, we're only going to have 25% of the stuff. And it says we're losing 75%, which means we have 25% left. So it's going to be 2 half-lives. Our time is 12.26 years, so it's going to be 24.52 years is going to be our answer. That was really short, but it's just a different way of phrasing the question. Okay. Number 42, we have a half-life. How long before only 1/16 of the original sample remains? Well, again, all we have to do now is say, well, at time 0, half-life 0, we have the whole thing, 100% of it. All right. Later on, after one half-life, we'll have a half. We'll have a quarter. We'll have an eighth. We'll have a 16th. All right, so that's how much remains. And that's a 1, 2, 3, 4 half-lives to get there. And our half-life is 3.82 days. Okay, so I just have to keep adding. Or I could just say 3.82 times 4, and that's 15.28. So I can just stop right there, I'm done. Or if you feel like doing this all out, you can do that, 7.64 and 11.46. Just keep adding the 3.82 over and over and over again. Either way is fine, but your answer is going to be 15.28. And we're talking about days. Okay, number 43. We have a 4 kilogram block. We're going to do our same thing. We have half-life. We have time, we have amount, we're starting at time 0, and at the beginning we have 4 kilograms, which has a half-life of 14.3 days. So one half-life is 14.3 days, and we only have 2.0 kilograms left. Right? It's stored for 57.2 days. So let's see how far down here we have to go. We have 14.3. That becomes 28.6, then 42.9, and 57.2. We notice that's 2, 3, 4 half-lives. So if we took the 4 and we multiplied by 14.3, we would get, in fact, 57.2. Right? Anyway, how much do we have left? Well, that becomes 1.0, that becomes 0.5, and that becomes 0.25. So we have 0.25 kilograms, or 250 grams left over. All right, another one. These are all very similar. You should be able to work these without any trouble. You have half-life, time, amount, 0, 0, 1. Original sample contained 40 grams, 2.77 years. And it only contains 2.5 today. 20, 10, 5, 2.5. 2, 3, 4 half-lives. Right? So we take the 2.77, we take 5.54, we add 2.77 again, we add it again, we get 8.31, and we add it again, and we get 11.08. Okay? And that's that one. Okay, let's keep going. Oh, we've got some bombardment reactions. We've got 4 of these, and then we're done. Neutron bombardment of calcium 40, 40, calcium 20, calcium, neutron plus neutron 10 is going to give me 41 on top. It is going to give me, let's see, it says potassium 40, which is number 19, and we have to have 1 on top, and we have to have 1 on the bottom, so that is hydrogen. You'd seen that one before. I think you've seen this one before as well. This is aluminum, it's number 27, but aluminum on the periodic table is number 13. We hit it with an alpha particle. So that's going to give us a total of 31 and 15, right? Which gives us phosphorus 30. Phosphorus is P, it's number 15, it's got 30. And what do I have to have? Well, the bottom can't change, but I have to have a 1 on top. So that's going to give me a neutron. So I can have 31 on top and 15 on the bottom. All right, bismuth, 187, sorry, that's 197, and that's 83. So it happens when my brain works and my mouth doesn't. It decays to thallium, that's TL, and that's 193. And thallium is number 81. So I have to have a 4 on top, and I have to have a 2 on the bottom. Gee, that sure looks like an alpha particle to me. And for the final question, we have rubidium-87. Rubidium-87. And we did this one also originally, and it is becoming strontium-87, and strontium is number 38. So I have a 0 on top and a -1 on the bottom, and that's a beta particle. Ladies and gentlemen, we are done. That is it. So, thanks for paying attention. Thanks for doing this. Good luck on your test. We'll see you in class. Have a great day. You are done with chemistry. See ya. Bye-bye.